Good evening, or at least for me. I don't know when you guys will be watching this. This is going to be Wednesday's lecture. It is on titrations. We're going to, let's first talk about what we've got going on. So there's going to be a quiz on Friday. I will be back on Friday. I'm driving, so I'm not going to get stuck in the airport somewhere. Um, and there'll be a homework due on Friday at 7 a.m. and this one is actually going to go because you're going to have new material. You're going to have titrations to practice. So we're gonna do that. I think that's what we've got going on. Oh no, I want to remind you that there is an exam next Wednesday. Okay, and so we'll do a review in class on Monday. All right, so let's go ahead and start talking about titrations. So titrations are what happens in a titration. Okay, there's an experiment performed to determine the concentration of an unknown acid or an unknown base. All right, so if you want to determine the concentration of an acid, you're gonna add a base to it. If you're gonna want to determine the concentration of a base, you're going to add an acid to it. Dr. Livingston says you did this about a week ago or a couple weeks ago, and you used what's called an indicator. An indicator is a chemical that changes color with pH. All right, so it changes color with changes in pH. And you know, the definition of indicator is more broad than that, but that will work for us right now. We'll limit it to what we're talking about. All right, and then so when we do these titrations, we're going to be concerned with two different things that I'm going to want you to know. So what can we get out of a titration? And the two things we're going to look at getting out today is we can find the concentration of the acid or base, whichever one we're trying to figure out. Actually, we can find whether the acid is polyprotic or the base has more than one hydroxide. How many, so find out how many acid protons are on the acid, how many acidic, let's call it, protons, or find out how many hydroxides are in the base. Okay, and then finally what we can do is we can actually determine the pK or pKb. All right, so those are the things we're after in terms of learning today. So let's go ahead and set off. What we're going to do is we've got this first example here, which is a titration of a strong acid with a strong base. This is a monoprotic acid when we look at this. So you could imagine, I'm going to make a problem out of this because I didn't have enough problems I liked at the back of your book. But let's, I'll make the problem in a second. But let's right now think about this is we're adding base. So we're trying to figure out what the concentration is of an acid. And so our reaction here, let's say it's HCl, is going to be reacting with, let's say our base is NaOH, so sodium hydroxide. And those two, when we have a strong acid react with a strong base, or we have an acid react with a base, we end up making water. Water is going to be liquid, and a salt. So in this case, NaCl, aqueous. don't want to widen out too much here. I know it messes up. Let's see if I can get this out. There we go. I know it messes up the way these things post. Okay, so we've got a strong acid and a strong base reacting here. And so what we have is the important thing we want to look at for this reaction here is we've got the equivalence point. The equivalence point is where, this is the position where all the acid has been consumed by the base. So in this case, what we've got going on is we have 50 milliliters. What we've got is the pH is low because we're starting with an acid, and then as we add base, it kind of goes up slowly as some of the acid is consumed. And then we get to this point where there's no more acid left, and then the pH jumps way up because now we're just adding base and increasing the pH of solution. Okay, that's the way this works. And so what we look for here is the equivalence point is going to be the steepest point of the curve. Let me write that down. I'll put that in red. So it's the steepest point in the curve. And these are titrations that we're doing here without an indicator. I told you what an indicator was up above. Your chapter introduces it. I know you've seen it in the lab. But here we've got a pH meter sitting in our solution, and we're measuring the pH as we go. All right, so we've got this. So let's say we have a problem. And the problem says, what is the concentration of hydrochloric acid of 30.0 milliliters of hydrochloric acid if it is titrated with, let's say, let's go with 0.532 molar sodium hydroxide, and yields the curve at the left. Okay, so we're going to take a look at that. And so what we can see here is that if we look at the curve on the left, that our equivalence point here is right here at this 50 milliliters. Okay, so I'm going to call it 50 point 10 divisions. Yeah, I'm going to call it 50.0 milliliters. I'm pretty sure that's a 50, not 51, 52, but I don't know really what the next digit is. So I'm going to call that 50.0 milliliters. So then what we have is a stoichiometry problem. We need to go from concentration of our base, we're actually going to go to volume of our base, to concentration of our acid. So this is going to be a milliliters to moles to concentration problem. So in other words, milliliters of base goes to moles of base, goes to, and actually, if we want to put all our steps in here, it's going to be milliliters of base, goes to liters of base, goes to moles of base, goes to moles of acid, goes to molarity of acid. And we're going to have to do some conversions here on both sides in terms of going milliliters to liters. So let's go ahead and do that. So I have, let's see, I have 30 milliliters. Oh, actually, hold on. Let's start with milliliters of base, not milliliters of acid. So I have I have 50.0 milliliters of base, so sodium hydroxide, and I need to get its liters, so if I have 1,000 milliliters, that's 1 liter. And if I have 1 liter of base, so this cancels with this. If I have 1 liter of sodium hydroxide, I'm just going to do a B, base, base, base. Excuse me, if I have 1 liter of base, this is my concentration of base up here. So that means I have 0.532 moles of base. Okay, and we see if we look up at our equation that 1 molecule of, or 1 mole of HCl reacts with 1 mole of sodium hydroxide. So if I have 1 mole of base, it reacts with 1 mole of acid. Moles of base cancels with moles of base in terms of units. And then if I have, and now this is going to pop out moles of acid here. All right, so a couple different ways we could do this. We could pop out moles and then we could divide it by volume, because we know that molarity is equal to moles divided by liters. Or we could just go ahead and put our volume down there. And I think that's what we're going to do. But we are going to want this milliliters to be in liters for that. So let's do that conversion. I have 30.0 milliliters, and I know that I have 1,000 milliliters. That's equal to 1 liter. Okay, and if I put that into my calculator, I'm going to end up with 0.0300 liters. All right, so I'm going to say that I have 0.0300 liters of acid, which is HCl in this case. I'm going to look around for my calculator. Lost it here on my desk and where I'm standing. Here it goes. Okay, I've got that. And so I'm going to go 50 times 0.532 divided by 1,000 divided by 0.03. And what I get out of that is I get my concentration of acid is equal to 0.887. I think I gave myself 3 significant figures and everything, so that's what I'm going to do with that. Molar HCl. Okay? And so that would be my first problem. That's how we use this, the titration of a strong acid with a strong base. We're not going to find the equivalence, or we're not going to find the pKa here, because for a strong acid fully dissociates, and so you're not going to be able to you can't figure out the pKa for that. There really isn't a pKa for strong acids. And then in terms of how many protons are on the acid, we'll figure that, or hydroxides. We'll get to that in a little bit. Okay, so now our next question is we have the titration of a weak acid with a strong base. We're going to do the same sorts of things here, where we have, we have our pH down here. Let's see, give me a better arrow. I don't have, that's not a better arrow. Give me an eraser. There we go, my eraser. So we've got the pH starts low, we got base, it goes high, and we have an equivalence point that has a nice sharp peak there. And so we can solve for that. We can also solve for the pKa here, and I'll show you how to do that. So our problem here would be, let's say, so it's a weak acid. Actually, looking at the curve, I think I know what acid it is. So I'm going to say that this is acetic acid. So acetic acid. And that acetic acid is going to react with a strong base. So let's just use sodium hydroxide again. It's always going to be a monoprotic base here. This is going to be, because it's a strong base we're reacting with, we're going to go to completion here. I'm going to write, because I'm a little running out of room here, I'm going to write down here at the bottom the other half, the reactant side of the reaction, which is CH3COO minus, okay? And that's going to give me, that's going to react. So I get I don't get water in this case. Well, I do get water. I get, this is going to actually be sodium COO minus, right? So I could put, I think I'm going to, I get the organic chemist in me, which isn't much. I'm not an organic chemist, but I have some tendencies. This is going to put, I'm not sure how I'm supposed to write this. Maybe I write the sodium here because that's where the negative charge was, or sodium acetate. That's what it's called. but I'll put my sodium here. Okay, and then that's going to be aqueous, so that's my salt, and we make water, like we've talked about before for these. Now I'm going to go ahead and write a problem for this. So calculate the concentration of acetic acid. Let's make it, what do you guys want to do? 40 milliliters? Let's do 40 milliliters. 40.0 milliliters of acetic acid if the concentration of sodium hydroxide let's go ahead this time and let's make it 0.251 molar. Okay, also determine the pKa. For acetic acid. Okay, first part of this problem is the same as the last one we did. We'll work it again. And then the second part of the problem, I will show you how we do it once we get there. I can show you now, but I'm not going to. All right, so what we have here is, once again, we have a problem. We've got acetic acid reacting with sodium hydroxide. Our equivalence point is once again at 50, so we're going to call that at 50.0 milliliters. I'm reading this off the graph, okay? Unfortunately, from your book, I guess that probably all these will be 50. They're not always going to be 50, so please don't internalize the 50. If the equivalence point here was at 33, I'd have to use 33. Okay. All right. So we're going to do this again. We said 40 milliliters of acetic acid. Let's quick put that into liters. 40 milliliters. If I have that, 1,000 milliliters is equal to 1 liter, and that's going to give me 0.0400 liters. All right. So my problem here then is I have 50 milliliters. 50.0 milliliters of sodium hydroxide. I'm just going to say base because it's faster to write, and I'm lazy. So then I've got 50 milliliters. If I had 1,000 milliliters, got to put this in liters. Then I would have 1 liter of base. Milliliters cancel milliliters. If I had 1 liter of base, the molarity is 0.251 molar, so I would have 0.251 moles of base. Okay, liters of base cancels with liters of base, and then if I had, and then we look up for how these things react. Okay, I've got moles of base. I need to figure out how many moles of acid that corresponds to. If you look up here, 1 mole of sodium hydroxide reacts with 1 mole of acetic acid. All right, so that's easy. So now we're going to go ahead and, so if I have 1 mole of base, I have 1 mole of acid. Moles of base cancels with moles of base. And then now I've got moles of base, and I need to divide by liters of base, or moles of acid, I'm sorry. I have moles of acid. I need to divide by liters of acid. And then I will have molarity. And I figured out up here that I had that many liters, so 0.0400 liters of acid. Moles of acid divided by liters of acid is molarity of acid. So I'm going to take 50 times 0.251 divided by 1,000 divided by 0.04. And what I get out of that is 0.314 molar acetic acid. Okay? Now, the question asks me what the pKa was for it. Well, if you remember, when we talked about the Henderson-Hasselbalch equation, we said that if we have an acid, that the pH is equal to the pKa plus the log of my acid concentration, I'm sorry, not my acid concentration, of my base concentration over my acid concentration, like that. When these two things are equal, that's the log of 1, right? So let's rewrite that. That's equal to the pKa plus the log of 1. If you put the log of 1 into your calculator, you'll find out that the log of 1 is 0. And so what that means is when the concentration of my acid and my conjugate base are equal, that my pH is going to be equal to my pKa. Okay? When A minus concentration is equal to HA concentration, like that. All right, so how do we use that up here? Well, at the equivalence point, all the acid is gone. So what that means is this is all A minus. We've turned all our acid into the conjugate base. So here at halfway between, so at 25, halfway between the equivalence point and nothing, we're going to have half the acid is gone. And so what that means is HA here is going to be equal to A minus, and that means that this is where our pH is equal to our pKa. So if I want to go across and read this, I would do it with like a ruler or something if I had one. I could do a sheet of paper or something. I'm going to read that as 4.75. I'm being a little influenced by the fact that I know what the pKa is. So I'm reading the value off the y-axis here to get the pKa. All right, so that's why I thought it was acetic acid, because I could look at it and see the pKa was about 4.75, which is what I know the pKa to be. The pKa equals 4.75. Okay, all right, so the next one. Now we're going to look at a diprotic acid. All right, we're going to assume that this one is H2SO3. I don't know that it is or not, but I know that it has 2 protons on it. I know it's a weak acid for both of those protons. We're going to react this with base, NaOH, and it's going to go ahead across, and it's going to make, we're going to react it with 2 NaOHs for the full reaction, but I guess we could draw out the reaction both times here. Okay, so we have, we're going to have the first reaction that gets us to the first equivalence point is going to make us HSO3 minus. Plus a water. It is going to be an Na because we have to have a counterion with it. And then our next one is going to be NaHSO3 minus, reacts with another NaOH. And that's going to make us an Na2SO3, like that. And I'm going to go up here. I'm going to erase these charges because the sodium cancels them. And then aqueous plus another water. Okay? And overall, you could add these together and have both protons go away. But this bit right here, this first reaction, this one, is for this equivalence point. So that reaction's all happening in here. And this reaction here is for this equivalence point. So that second reaction, let me color code these. That second reaction right there is all in here. Okay, so there's our second reaction. And so now we want to figure out what the concentration is. So I could write a reaction here. I could say, what is, determine the concentration of, gosh, I don't even know what that's called. This has got a sulfite in it, sulfuric acid, sulfurite acid. I don't even know what that is, so I'm going to have to just say H2SO3. I'm sorry, I should know the name of that, I guess, but that's a little embarrassing, but not too terribly. But H2SO3, if let's say, let's go with 25.4 milliliters of it reacts with, let's go with 0.221 molar sodium hydroxide. According to the titration curve at left. Alright, so what would I recommend you do here? So here they've identified the equivalence points for us. They once again put it at 50 milliliters. I wish they would have kind of varied that a little bit more. These are actually where they were just showing in the book, demonstrating the concept. So I don't blame them for that, but I do blame them for the fact that they didn't have enough good problems at the back of the book for this. Alright, so we know that our equivalence point is, I could do this problem twice, I don't want to, so we could do our normal problem, and if I'm going to get the same, if I use this equivalence point, okay, and I assume that I'm just looking at this reaction, okay, I'm going to get the same answer as if I add those two reactions together and I use this equivalence point. I'm going to do the second, okay? So if I add the two reactions up above, I'm going to add these two reactions, okay? I'll do that down here really quick, and then we'll just use the second equivalence point here. All right, so I've got H2SO3 aqueous plus 2NaOH. So if I add those two together, I got an NaOH in both of the reactants. And then also what happens is, let's see, we're reacting with a strong base, so these are going to go to completion. And I hope you see that this here is a product on one reaction and a reactant on the other, so they're going to cancel out. And then I'm going to have two waters, one for each reaction for products. So I've got that reacting with 2 NaOH, and that's going to give me an Na2SO3. That's my salt. Make that aqueous, and then I'm going to get two waters, like that. Okay? All right, so now we can look at our second equivalence point is at 100 milliliters. Once again, this is your book, just picking a super round number and using the same example each time. That could be any number. You would be looking for the steep part of the curve here. So here, the first equivalence point is because this is the steep part of the curve. First time we see kind of steep part, and then here is the second time we see a steep part. All right? And so I'm going to use the 100 milliliters, and it's going to react with 25.4 milliliters of H2SO3. Let's go ahead and make this milliliters into liters, and the other one we'll just do in our dimensional analysis. So if I have 25.4 milliliters, and I go ahead and if I have 1,000 milliliters, and I react that, it'd be 1 liter, right? So I'm going to go ahead and cancel these two, and then I'll rewrite it down here. That's going to be 0.0254 milliliters. Great. So that's our milliliters of our acid over here. All right, so now if I have 100 milliliters of, I'm going to call that 100.0 milliliters of NaOH. All right, and if I react that, and if I have 1,000 milliliters of, I'll go back to bases because it's faster to write, of base, that's 1 liter of base. And if I have 1 liter of base, looking up here, I have, that's my concentration, so 0.221 moles of base. All right, so here's a trick we haven't encountered before. 2 moles of base reacts with 1 mole of acid, right? So we need to do that. So if I have 2 moles of base, then I'm going to have 1 mole of acid. All right, and then I have my milliliters of, that's not milliliters, that's liters because we converted it. I have my liters of acid over here. And so I have 0.0254 liters of acid. All right, and then I have milliliters of sodium hydroxide, concentrates, milliliters of base here, liters of base, moles of base, moles of base, moles of acid over liters of acid gives me molarity of acid. So now I'm ready to put that in my calculator. So I have 100 times 0.221 divided by 1,000 divided by 2 divided by 0.0254. Okay, and so that gives me 0.435 molar H2SO3. Okay, that is the concentration. That's the question's problem. One other problem I could have asked here: what are the pKa's for the first deprotonation and the second deprotonation for H2SO3? So what are the pKa's for the first and second deprotonations of H2SO3? I'm going to go ahead and put a question mark in there. I'm going to cut, since I don't have to do subscripts, I'm going to go and grab this. Oh. What exactly happened there? Okay, great. So we're going to go ahead and copy. I'll try it one more time here, and then I'll give up and write it in a second. Okay, and the way we do this is we look at the half equivalence points. So our first equivalence point is 50. So our half equivalence point is going to happen at 25. We'll carry that over, and that looks to be about, let's call that pKa 5. Right. Yeah, it looks about 5, I guess. And then we're going to bring this one up. Our second equivalence point is going to be here, and look at that, pK of 8. Right, because that one's right on the line. I can follow that one right across, even with my bad writing. See, the line even helped me make that straighter. So our answers down here would be 5.0. I think I'm going to go with 5.0 for that, and it would be 8.0. Okay? All right. Now, what happens if we're doing the reverse? Well, the reverse is like what we just described, except that the curves go down instead of going up. So what if we titrate a base with an acid? Like what we can see here. Well, this is what we just looked at, our titration of a strong acid, a weak acid, and a diprotic acid with a base. And if you do the reverse, you end up with kind of the inverse curves. Here we have a strong base being titrated with a strong acid, Here we have a weak base being titrated with a weak acid. I'm sorry, here we have a weak base being titrated with a strong acid, always titrating with strong. And here we have a dibasic compound, it's saying a dibasic base, so it's got two OHs, I'm going to say, being, it could be slightly different than that, being titrated with a strong acid. Okay, and so I'm just going to write, just make sure we're aware of this. That's strong. And so it's just the same thing, except that we're reversing which is which. All right, and then if, just to do this now without, we did one of these where we weren't able to see where that pKa was, but so for the weak acid, right, if we wanted to know where that pKa was for this one, right, that would be, I'd carry that over, hopefully better than what I just did, and I would call that 9.0. So the pKa here is 9.0. Oh, wait, no, not there. Sorry. Let me back up. The pKa is at the half equivalence point. Almost had to like send out a correction after one of you caught it. So this is the equivalence point, and this is the half equivalence point. So actually it's the same graph as before, so the pKa is probably 4.75. Same sort of thing. But let's go ahead and do the weak base. So let's figure out what our pKb is. So we have, here's our equivalence point right here. Half our equivalence point would be, did I do that badly up there? Maybe. They're pretty flat, so it actually saved me to some extent. So I need to go one of these, right? One of these, and then half of half again. So it's going to be about here. That's halfway to 0. And so that to me looks like 9.5. So pKb, or no, it's going to be pKb equals 9.5. Alrighty. Let's try this problem. Match each graph to the correct description. So we've got the titration of a strong base with a strong acid. We've got the titration of a weak acid with a strong base, and then we have the titration of a dibasic compound with a strong acid. So when I look at this, graph 1 has two equivalence points, right? We got a steep thing here, and we've got a steep thing here, and what that tells me is that this one is C. Okay. Now I'm looking for a weak acid with a strong base. Well, here they've got so this one has to be that, because we're going with a strong base with a strong acid. We're going from high pH to low pH, right? As you add acid, the pH goes down. And then the titration of a weak acid with a strong base. They made this one easier than I would have thought. Is that. Okay, and the way you can tell a strong, if it was a strong acid versus a weak acid, is you've got this little curve. It's a little more slopey. I'm not going to do that to you. Okay, so it'll be obvious. I like the way they worded this problem. I think they actually chose well. All right, final problem for us. So here what they did is they gave data for problem 76 in your book. They said a sample of barium hydroxide is titrated with hydrochloric acid. The pH at different points in the titration are listed in the table below. We don't have two pKb's, so I wonder if barium hydroxide, is that one of our exceptions? Is it a strong base? Maybe it's an exception in a strong base. I'll look it up later, but because we don't have two protonation or two hydroxides coming off here, right? You just see one. Yep, and we end up way down at that low pH. So I'm going to assume it's a strong base, actually. So it's a strong base with a strong acid. What our reaction will look like is it's barium hydroxide, right, reacts with, and it's going to have to react with two hydrochloric acids. to give us, we're going to end up with barium chloride plus water. Okay, the two waters. All right, so that's what that looks like for our reaction. We have 20 milliliters of barium hydroxide with 0.1 molar hydrochloric acid. Let's go ahead and put this in liters because we're going to want that later. So 20.0 milliliters. If I have 1,000 milliliters, I'd have 1 liter. And so that gives me 0.0200 liters. All right, we'll want that in a minute. And then we're going to look at this data. I took the liberty of plotting it. And what I'm looking for is my equivalence point. What is it? It's asking me for the... It's just asking for the molarity of the sample. And because I'm pretty sure, based on looking at it, the base is a strong base here, we can't figure out a pKb for it anyway. But it looks to me like this point actually landed in the middle enough that I'm just going to read it over there. So this pH 7 right there looks like the steepest part of the curve, also arguing that it's a strong base. If that point lands on pH 7, probably a strong base or a strong acid. And that's 32 milliliters. So I'm just going to take the 32.0 milliliters of acid. So we're titrating the acid with the strong base here, or the strong base with the acid here, which is actually pretty good for us because we haven't done a base to acid one. So we took 32 milliliters, right? So 32.0 milliliters of acid. And if I have 1,000 milliliters of acid, I have 1 liter of acid. Milliliters of acid goes with milliliters of acid. Okay. And if I have 1 liter of acid, they gave us the concentration of our acid up here was 0.10. So 1 liter of acid, I'm going to have 0.10 moles of acid. That cancels. And then now we need to look at our ratios here. 2 moles of acid react with 1 mole of barium hydroxide. So 2 moles of acid is going to give us 1 mole of base. Okay, and now we could just put our volume of base in here, right? And we figured out our volume of base right here in liters was 0.2 liters because we read the 2 milliliters out of the problem, which is right there. And so 0.0200 liters of base, and that's going to give me my molarity of base. And so now I'll put this into my calculator. 32 times 0.1 divided by 1,000 divided by 2 divided by 0.02. And I get out of that 0.08. How many sig figs did I have? Probably 300 molar barium hydroxide, because that's what we were solving for, the amount of base. Okay. All right, well that's it. Those are the sorts of problems you need to be able to work. I'm going to give you some of those. We'll see what the Achieve system has for that, and I'll give you some of those to work. And I will see you guys on Friday. We are going to have a quiz on Friday. Don't worry, and I'm driving back, so I'm not going to get caught in the airport. So plan on that quiz. Reach out to me if you have any questions. Hope you guys are doing well, and I'm looking forward to seeing you on Friday.